Hey everybody, happy Thursday. You are almost through the week. Um, Hope you have been having a great week. Um, just wanted to, the plan for today is to go through some review problems. There's no quiz today because we've got an exam on Monday and I didn't want to give you both of those. So I'm going to go through and kind of give a broad overview of the sections that we've covered, some types of problems that we may encounter. And then you've got some review problems to work on over the weekend. And again, I'm going to give you some solutions to those. Don't consult those solutions right away. Really try to work through those problems first. And if you get stuck and you're like, I don't really know how to proceed, you could consult the solutions. But it's going to be best if you try to do as much of it as you possibly can on your own. Okay? So just to review, the overall sections that the exam is going to cover are sections 3.7 through 3.9 out of chapter 3, and then sections 4.1 through 4.5 out of chapter 4. Okay, so chapter 3 was on applications of derivatives, so we still have a few applications of derivatives that I want you to remember. So the first one, section 3.7 was our friend optimization, which is our word problems, okay? Just to remind you, remember that the key word here is it'll say we want to maximize or minimize something or find the largest or the smallest, okay? And our steps here were that we write down we want to maximize or minimize some variable, and then we find a formula for that variable. That variable equals something. And then usually we'll have several variables in here. Like if I want to maximize the volume, I have a formula for the volume, but the volume might have two different variables in there that I don't want to have two variables. So then I use other information to eliminate a variable so that I get this down to one variable, and then I use calculus to find the max or min. So in other words, I take a derivative, set the derivative equal to 0, solve, and then check. Okay? So those are our optimization problems. That should, and there's at least one on the review problems there that you can take a look at. Okay, second section out of 3 that are there from from chapter 3 is Newton's method. Okay, remember, in order to do Newton's method, you're probably going to want to have access to your calculator. Okay. The point of Newton's method was finding zeros of functions. Where does a function equal 0? And we had this technique that we would start with an x1 equals something. And then the way that you get the next one is you take the previous one minus f of that number over f prime of that number. Okay, so you have to calculate, given the function, you have to figure out if x1 is 2, then you plug 2 into the function and 2 into the derivative, and then you do 2 minus f of 2 over f prime of 2, and that's going to give you this next technique, the next point, x2. Okay. Recall, one thing to just remember is that sometimes this technique fails. This does not always work. Okay, sometimes this leads you to bounce around and you don't actually end up getting a derivative at all. Okay, you'll get another point here. Okay, last section from chapter 3, section 3.9, which is on differentials. Okay. This section actually dealt with two different things. One of them was what we called linearizations. Okay, the idea here is that if I wanted to plug a number into a function, and plugging that number into the function is very hard, what I do is I find a place nearby where plugging into the function is easy, and then I take the tangent line, and the tangent line is easy to plug in. So we had example like, if I want the square root of 99.4, the square root function is really hard to plug 99.4 in, but it's very easy to plug in the square root of 100. So what I do is I find the tangent line at x equals 100 to this function, and then I plug 99.4 into the tangent line instead of plugging 99.4 into the actual function. Does that make sense? So let's maybe just let me do this example here just to kind of, because it's probably been a little while since you've looked at these. If I take the function square root of x, and then I look at x equals 100, let's find the tangent line to square root of x at x equals 100. Okay, here's that tangent line. Okay, the way that I get the formula for the tangent line is I need a point. Well, x equals 100, the y, if you plug 100 in, the square root of 100 is 10, so we get a point. And to get the slope, we take the derivative, and the derivative of x to the 1/2 is 1/2 x to the minus 1/2. In other words, 1 over 2 root x. And so if I plug in, if I want the derivative at 100, that's a derivative everywhere. If I want the derivative at 100, that's going to be 1 over 20. So the tangent line is y minus y1 equals slope times x minus x1. In other words, the tangent line is y equals 10 plus 1/20 x minus 100. That's this tangent line at 100 as opposed to the function near 100. So the idea is now if I need to evaluate the square root of 99.4, instead of plugging that into the function, which is really hard, I'm going to plug it into the tangent line, and that's going to be much closer. So I'm going to plug in, so the square root of 99.4 is basically going to be what I get when I plug 99.4 into this tangent line. Okay, 99.4 minus 100 is negative 0.6, so I'm going to get 10 minus 0.6 over 20, which is going to be 10 minus 0.03, which is 9.97. Okay, now if you were to do this in your calculator, you would actually see that 9.97 is really, really, really close. So one of this tangent line, using tangent lines instead of using functions, is called linearization. We've basically taken the function and turned it into a line by using the tangent line instead of using the function. Okay, that's what this thing is right here. We would call this the linearization. It's the tangent line. Okay, so using tangent lines to solve problems on functions is called linearizations. That's one thing that was in this differential section. The other thing that was in here is calculating or finding error. Okay, you remember that if we had a problem like I measure the radius of a basketball to be 1 foot, but it could be off by 0.05 feet. And if I use that radius, number to calculate the volume, if the radius is off, then the volume is also going to be off. And the question is, how far off is the volume if the radius is off by some amount? So what we did there is we had a formula for the volume or whatever it is we were trying to calculate. And then we use differentials to come up with a formula. So dV dr, the derivative here in this case is going to be 4 pi r squared. So the error in the volume is going to be 4 pi r squared times the error in the radius. So what we can do is we can substitute our possible error in the radius and the actual value of the radius to get a possible error in the volume. And that allows us to accommodate for how far off the volume could be. Okay, so hopefully this is bringing back some memories of some things that we talked about in at the end of chapter 3 there, okay? So that's chapter 3. That's probably the stuff that's going to feel less familiar. And then chapter 4 is going to feel more familiar here. Okay, starting with, so section 4.1 was on antiderivatives, and we've been doing a lot of antiderivatives lately, so this should feel pretty comfortable. So you should know, for instance, here, how are two antiderivatives for the same function related to each other. Okay, this is where our plus c comes in. If I have two antiderivatives for the same function, if two functions both differentiate to the same function, these two are off by a constant. Okay. Remember that our notation for antiderivative was the indefinite integral. Okay, so there's no limits of integration there. You should review the differentiation rules because we're reversing those to get the anti-differentiation rules. Okay. The one to remember here that's a little bit odd is x to the n. When you anti-differentiate that, you get x to the n plus 1 over n plus 1, again, assuming that n is not negative 1. If n is negative 1, then you're talking about a natural log here. Then the antiderivative is natural log of absolute value of x. Make sure you remember that absolute value. Okay. One thing also to keep in mind is you may need to multiply or divide before anti-differentiating. So for example, if I had x times x minus 1 dx, don't anti-differentiate each one of those separately. That's not good. Okay, you can't do that. And the last thing to remember from this section is we did have some examples where, for instance, the second derivative was 5, and I said, well, what's the original function if the first derivative at 0 is 1 and the function at 0 is 3? So what you do is, if the second derivative is 5, then it came from 5x plus some constant, and then you use this information. This is the second derivative. You use this information about the first derivative to figure out what that constant should be. In this case, the constant would be 1. And then you use that information to back up and say, okay, there's some other constant here. What should that constant be based on this information, okay? So that's, again, some problems that we did when we were first talking about antiderivatives in section 4.1. Okay, section 4.2. This is where we get into our fun sigma notation and areas. Okay, so under sigma notation, I would expect you to be able to write out sigma notation, to write something in sigma notation. So you should be able to expand something out and write something in sigma notation that shows up. And then you should feel comfortable, you should know how to manipulate sigma notation. So in other words, we pull out constants and we separate sums. We've been doing that, so you need to feel comfortable doing that with sigma notation. When we talked about areas, we had a special set of steps that we did. We would, so if I want the area under a function from one point to another. Okay, we had kind of a set of steps that we did. We split the interval into n pieces. Okay, and then we get, draw the rectangles using right endpoints. Now you don't have to use right endpoints, but when we're doing this calculation, it usually works out easiest to use right endpoints. So, and then we add up the areas of the rectangles, and we put that in sigma notation and simplify. And then if we're just calculating, like if I say estimate it using 4 rectangles, then you don't have to take a limit here. Like if I give you a function and say use 4 rectangles to just get an estimate of the area, then you just cut it up into 4 pieces and do your areas, and then you get a number, and that's it. But if I want to say what's the exact area, then what we do is we do this in general with n, and then we take a limit as n goes to infinity. Okay. And probably, like what happened on the quiz, you're probably going to get at least one problem on the exam where I have you calculate the area using this process of sums of rectangles and limits of sums of rectangles, and then a process where you're using geometry. So that shouldn't be that shouldn't be unusual. Okay. All right. Section 4.3 then is Riemann sums, which is basically the same thing, indefinite integrals. Okay. So the areas of the rectangles, this piece right here is a Riemann sum. Now in general, Riemann sums you can use, you don't have to use right endpoints. We just kind of called the points where we're using these in general x sub I star. Okay, but we use the widths of the rectangles were always the same. We weren't changing those. That was the length of the overall interval over n. Okay. And then when you took a limit, that limit was the area, and the area is what we call the definite integral. Okay, that's the area from a to b under the function. Okay. Now remember one thing that we only do this for continuous functions on closed intervals. We have a theorem that said if you have a continuous function on a closed interval, then this limit will always exist. We don't have any sort of theorem that says in other cases the limit may or may not exist. Okay, so we're always assuming we're talking about a continuous function on a closed interval. Then we talked about some properties of these definite integrals. Things like if you go from a to a of a function, that area should be 0 if you start and end at the same place. Another one is that if you take the interval, if you go from a to b and then flip it and you go from b to a, you get a minus sign out front. So that's the negative of the original area. You can also, if you go from a to b, that's the same thing as going from a to c and then going from c to b. Similarly, if I go from a to b of 2 functions, I can just do each one separately. Similarly, I can pull constants out. Okay, so if I want the area of c times a function, it's just c times the area of the function. Another thing to remember is that it calculates, the definite integral calculates net, what we call net area. Okay, if you're above the x-axis, it calls it positive area. If you're below the x-axis, it calls it negative area. Okay. And then for special functions, before we had the fundamental theorem of calculus, if you gave me a line or a half circle, so something of the form r squared minus x squared square root, then you can use geometry to get this area. Using rectangles, triangles, half circles, we can use geometry to actually calculate those areas. Okay? All right. So then our final two sections, which are going to feel a lot more familiar now, are section 4.4, which is our fundamental theorem of calculus, which came in two parts. Part one said that if we start with a continuous function on a closed interval, and we define this new area function from a to x, then we get a continuous differentiable function that the derivative of that function, area function, is the original function back again. And one of the results of this was that all continuous functions have antiderivatives. Their area functions are antiderivatives. Okay. And the kinds of problems we saw here, I would give you like the integral from 0 to x of sine of t squared dt, and I would say, what's the derivative of that? And you just take the x and plug in. Okay, the only things to remember on this are that if I ended up giving you something that was like from 0 to x squared, if this was just x, the derivative of this integral would be the square root of e to the x minus 3. Just take x and stick it there. If you have x squared here, then you actually have a chain rule going on where you have an outer function like this, and an inner function of x squared. So in other words, you're going to differentiate the outer, you're going to get square root of e to the x minus 3, but instead of x, you're going to substitute an x squared. So you're still taking this and sticking it here, but you have to multiply by the derivative of that inner function in the case where you have something that's not x there. So that's part one. And then part two is that the way that you actually calculate that definite integral is you find an antiderivative and you plug in b and you plug in a. So calculating definite integrals basically reduced to finding antiderivatives, which is much easier than Riemann sums. It's much easier, much more general than just using geometry in certain very specific cases. Okay. And then the last one is the section that we've been talking about here, substitution. This is kind of reverse chain rule. Okay, so you're looking for, you're trying to do antiderivatives, and you're looking for two different things. You're either looking for composition, and when that happened, we would let u equal the inner function, or we would look for the du. What we meant by that was look for something that's a derivative of something else in the integral. Okay. And remember that with this, when we did definite integrals, there were two techniques that we could have if we had the integral from like 1 to 2 of some function dx. If you go to du, you can leave those limits of integration there, but you have to keep writing x equals 1 and x equals 2 until you get back to x's and then sub in. Or you can substitute in for the actual numbers and convert everything to u's and not go back to x's. So just keep that in mind. And we had those two properties about even and odd functions. So if you have an odd function and you're going from negative a to a, that's just 0 if the function's odd. If it's even, it looks the same on both sides, so you can just do one side and then go from do twice that. So if the function's even. If it's neither, or you're not talking about going from negative a to a, don't worry about that property. You can't use it. Yeah. So this should kind of give you an overview. Hopefully it's not overwhelming. But take a look at the review problems. You've got some time in class today to take a look at those. Again, the solutions are posted too. Ms. Barbo is there to answer some questions. If some other questions come up over the weekend, you're welcome to send me an email. I can't guarantee that I'll be able to get to the email, but I'll do my best to try. And I will be praying for you guys as you prepare. I know that this is not your only class that you're preparing for as well. There's a lot of other things going on. So I'll be praying for you guys, and I hope that you guys have a great weekend, and I'll see you all on Monday.